We can wait a little bit until people come. It's okay.
Yeah, that's fine. That's fine.
5 minutes, just like 5 minutes.
Yeah.
The people from India is coming already or not? Okay, so 1 minute is already. We can start after 1 minute.
Okay.
Okay.
People from India have arrived.
Okay.
Hello, Mr. Hari.
Okay.
Hi. Good morning.
Good morning, everybody. Nice to meet you.
Good morning.
And thank you for your comment. And I hope we can have a good family for energy power and solar energy. And Mr. Amarjit is the big professor and my partner and my big brother. And I'm really glad to have him. And we're going to start. Everybody explain about himself for 1 minute or 2 minutes. For me, my name is Zaad Mubarak. Original have Iraqi and Brazilian. We work in the solar energy long time, and also we work by the oil, and also we work by the summer project for the industry, and also we are happy we have a very good team. I'm also work with my partner, Mr. Ibrahim from Oman, and please you can join yourself one by one, explain about yourself. Great. Nice to meet you.
Shall I start with me?
Yeah, please go ahead.
Yeah, this is Hari Krishna from India. I'm based out of Hyderabad, and I have two companies. One is into IT consulting and defense and aerospace. And I have one more company which is into renewable energy. Basically, predominantly, we have a product hybrid renewable energy system wherein solar plus vertical axis wind has been integrated together. We have around 18,000 installations across India. And also, we are likely to start operations across the Middle East as well as the African territories. We already have customers in Africa and Middle East, but still we are going a little aggressive coming this year. And we are keen on that the new product which was shared by Mr. Kishore, as would like to understand the specification of that product, the parabolic solar system with the BESS. That's a product we are keen on looking at. And we have so many other opportunities where we can propose this product and take it forward. Yeah. And we also into SMRs, small modular reactors. We signed up with a company from the Romania, and we are proposing these products in India. That's a brief about me. Thank you. Thank you very much.
Yeah, it's open. We on the meeting. Yeah. Oh yeah. This here.
Okay, I'm coming.
Okay. Yeah. Okay. Yeah, please go ahead. The voices go.
I'm coming.
Hello. I don't think.
Yes,
Yes, you are inside, right?
I'm coming in. I'm coming in. I'm coming in now.
Okay. I don't hear. Why? I mean, but I don't know why I don't hear. Yeah. Open the speaker. Did I close the speaker or
Directly from there.
open everybody?
He's on mute.
Yeah. Okay. Now I hear. Okay. Open him. Why he's open? Open for everybody. Sorry. It's from you. It's not from us. It's a mute from you, not from us.
Yes, everybody's on mute, Zab. They need to open their speaker, their microphone.
Yeah, we
Okay,
all.
now, am I clear?
No, please again, because you always have a mute. Already
No
we open
problem.
everyone. Okay.
Okay, I just want to know if you're hearing me now.
Yes, we hear you now. Please. Go
Okay,
ahead.
great. Okay, hello everyone. It's Pat Cluthe from Windcatcher International, based out of Toronto, Canada, and Anderson, South Carolina, USA. We're a small startup renewable energy company that combines wind, solar, and geothermal as a multi-system stage for independent supply developments. We're in a basically a concept development stage to where data is being delivered now, and we will be manufacture ready in 2027. Our scale system will be to
Please.
Are we on?
Yeah, go ahead, please.
Okay, our scale system will be for independent operators. We will not be our systems will not run through the grid, supply to the grid, off the grid. It will be these systems will be completely independent. So they'll be marketed and they'll be controlled by the customer and or end user. It's a very simple idea, and it's based on fixing a very broken system, which the grids are now, that will never be able to handle the capacity of the 22nd century. Thank you.
Thank you. Okay, next, please. Go ahead. Okay, please go ahead. Next one.
Hey guys, good day. My name is Sasha Singh from DNS Group here in Toronto. And our background is real estate development and construction. We're into agriculture as well as healthcare. We also are in oil and gold as well. And we're highly focused as well on energy. And, we're here today to learn some more too as well. And Pat, who went previously, is part of our team here in Canada. And we're looking forward to get some more information so we can move forward.
Hello.
Yeah, please. Next. Yeah.
My name's Excellency Anthony Kwaku. I'm the president of Club Diplomatic International Africa.
Nice to meet you.
Yeah.
Okay. Next.
Yeah, I'll go now. And my name is Chris Parthiban. I'm part of Shasha's team. I'm involved in the telecommunication, particularly the data center side of it. Data center in the lifeline right now is the power, which is very scarce. Therefore, it's a lot of delay and everything. My interest is how your power generation and storage system can help the growing data center demands.
Okay. These guys next.
Shall I?
Mr. Ibrahim, you don't.
Yes.
You don't speak.
Good morning, everybody. I've said this is Ibrahim Murad Al-Balushi. I'm an Omani. I'm from Oman, and Oman is in Middle East. Maybe some of people, they don't know where is Oman. We are specialized into packaging, corrugated packaging here in Oman, and we have some printings, and we involve in different business, real estate, fuel, and others. I've been honored just to be one of Mr. Saad's partnership here in Oman, and we're going to already started, you can say, started our factory here in Oman in industrial area. It's called Madain. I said I will speak in the end because normally we welcome our guests. So let me to see at the end actually. Thank you for all being with us here. Saad, I think we can start.
Yes.
Thank you.
Thank you for everybody. Please, Mr. Amarjit, can start, please.
Yeah.
Okay, please.
Kindly, we request everybody to mute the mic because as soon as someone speaks, it distracts the others.
Okay. Thank you, Saad. My name is Amarjit Riyat, and I'm the technology partner for EZ Babylon. And we've been developing some specific technologies for solar power as well as a storage system, right? And I will run through the details. Is there anybody else who needs to be introduced, Saad, or shall I go through the presentation?
Yeah, please just go ahead, please.
Okay.
Thank you.
All right, let me share the screen. 1 minute. Okay, can you see that?
Yes.
Okay. There we go. Okay, so our company is called Store Energy, right? We've been around for about 10 years, and we specialize in solar power and, as I mentioned, a thermal storage system. This company was set up by two people, myself and Marko Vuksanovic. I'm the CEO, and Marko is the Chief Technical Officer, and he's the main brains behind the technology, right? So what is our mission? So what we're looking at is to, as the world is now beginning to move towards transiting from fossil fuels into renewables, there are many issues which are arising, right? And so our view and our mission is to enable that transition to happen smoothly, right? And there are two big markets for energy. The first and the biggest market actually is for heat for industry. This market is actually probably double the size of power market, right? So if you look at industry, each industry requires some form of heat, whether it's the pharmaceutical industry, tires, chemicals, they all require heat. And at the moment, majority of that heat is given by fossil fuels, right? But as we're now moving forward, the need to reduce our dependence on fossil fuel is becoming greater, right? Yes, in the short term, we still need oil and gas, and we will still need them over the next 50 years. But the transition to renewable energy is becoming more and more prevalent, and especially in Europe, right, where there are a lot of incentives to move away from fossil fuels and into renewables. And the second element of our technology is power production, where there are two parts to the power production. Number one is actually producing power, which is 24/7, 365 days, and at a price which is cheaper than fossil fuels. And the second is as we get more and more renewable energy on the grid, there's an issue with grid balancing, right? And I will come on to that in more details. So those are our overlying objectives of what we're trying to achieve. So if we look at the existing energy production, right? So you have the renewable energy. For instance, the issue with solar power and with wind is its intermittency. So, 1 minute you've got 2,000 megawatts of wind power, and the next minute you don't have anything, right? And here in the UK, we have an issue that roughly in Scotland, 2 days every week, we have too much power. We have, and then what happens is the grid becomes unstable, and the grid operator actually will pay you to take the power down, right? So they will pay you something like £100 per megawatt hour to take that power down, right? And this is an issue with all renewables, right? And so one of the key aspects of renewable energy is you need some sort of storage, a buffer, which allows you to match demand and supply, right? And but at the moment, storages are very expensive. A battery storage, for instance, is roughly $120 per kilowatt hour, right? So you need to be able to store large amounts of energy at a cheap rate, right? And that's where we come in. And then finally, obviously, as part of all of this intermittency is the grid stability. Here in the UK, one of the other problems we have is when there is not enough solar power or wind power, they have to bring up what are called balancing systems, right? So these are gas turbines which they switch on, right? And they are very expensive, right? And so the need to have a stable grid is very much dependent on having a very cheap storage system which is able to download large amounts of energy and give out the energy in terms of heat or power when you require it, right? If we move on to the fossil fuels, the issue with global warming is something which now everybody's understanding. Here in the UK, for instance, we've got today the temperature is going to be 32 degrees, right? And we've had up to 37 degrees this last week. And this is happening all across Europe, right? We have forest fires in UK, we have forest fires in Spain, right? So this global warming is happening, and one of the ways to mitigate that, obviously, is to try to reduce as much of the fossil fuel as possible, right? Okay, so before I go into the details of our technology, let me just give you an overview of what we do, right? So you have here is your collector, solar collector, right? And I'll explain in details how that works. And from there, we take this energy, which we focus here, and that goes into our thermal storage, right? And from the thermal storage, we extract the energy to run the turbine and onto the grid or whatever you want, right? So what we're doing here is everything goes into the thermal storage, and you extract the energy from the thermal storage as and when you require, right? And the advantage of that is that you can have a 24/7, 365-day production because everything is simply extracted from the thermal storage. So there is no direct production. Everything happens to the storage, right? Now, this will be a typical layout for a 1 megawatt solar plant, right? So you have your various different collectors, right? And these are our 25-meter collectors, which we call concentrators. And the reason we call them concentrators is because they act like a lens, right? They focus the sun's rays onto one point behind the concentrator, right? And so you have your collectors, and then you have your thermal storage where everything goes into the thermal storage. And from the storage, you take the energy out from a steam generator, a turbine, and then producing electricity through a generator, right? And then you have your cooling towers, etc. So this is an example of how the technology works. So if we go into more details, this is the concentrator, right? So this is a 10-meter concentrator, right? So we have several models. So this is a 10-meter, we have a 6-meter, we have a 15-meter and a 25-meter, right? So here are the sun's rays, right? And they are focused onto this point at the back of the concentrator. And there we can achieve temperatures of something like 2000 degrees if we want to. Okay. From there, we use air from the outside, and we pass the air through this focal point, which then we heat the air up to 900 degrees, 1100 degrees, and then the air is then pushed into the storage, right? The concentrator is made out of mirrors, right? And these mirrors are concentric rings. So air passes through the concentrator, so we don't have any issue with wind speeds, right? With other types of collector technologies, when you have a very high wind speed, there's a possibility that the whole structure can fall over. We don't have any issues with high temperatures, right? So we can work in the Middle East, or we can work in other areas where the temperatures are not so high, but you have a very good solar radiation, right? For instance, with PV, one of the issues is that with very high temperatures, the PV becomes inefficient, right? So you have to have a certain temperature for the PV to produce the maximum efficiency. And this is a very simple structure, right? So it can be designed and produced anywhere, right? So the idea would be if you're looking to build a very large power plant, you can actually have manufacturing on site, right? So this is a 25-meter concentrator, right? So we have a collection surface area of 250 square meters, and it tracks the sun both ways, right? So both horizontally and vertically, right? So basically, we start taking the energy right from sunrise all the way to sunset, right? So it's a fully tracking system. It uses aluminium mirrors, right? And at the focal point here, we can achieve temperatures of over 2000 degrees, right? But we tend to operate at sort of between 600 to 900 degrees because we don't necessarily need to operate at 2000 degrees. When you're operating at very high temperatures, you need to have special materials. Stainless steel needs to be a special stainless steel, which increases the cost, right? So you have to weigh the cost and the power balance so that you're most economical, right? So those are our concentrators. I'm going through this, and then you can come back to me with more detailed questions, and we can go through more details of what exactly you may require further information on. So we have the thermal storage, right? And the thermal storage is a solid state storage, right? And we can go up to temperatures in the thermal storage of 1500 degrees. Right. Normally we store at about 900 degrees. Our heat losses are less than 0.5% a day. On the very large storages, we can get heat losses of less than 1% a week, right? There are no moving parts in the storage. There is no pressures. There are no hazardous materials, right? Once the storage is built and sealed, it has a lifespan of 35 years plus. There's no maintenance apart from painting the outside of the storage, right? And it's made from ceramic bricks, right? And these ceramic bricks can be manufactured anywhere in the world, right? And that is our patent, our IP. So the advantages of our technology are that we can give constant power. There are no fluctuations because we extract everything from the storage. It can be used as a base load power because we can give you a base load there 24/7, 365 days. We can achieve very high temperatures at the focal point. It has lower build cost because it's a modular build. And the byproduct of the storage is that we have waste heat at over 100 degrees, and we can use that for water desalination or cooling using absorption coolers, right? just a quick overview of the storage, right? So our thermal storage costs roughly about £10 per kilowatt hour, right? Molten salt, which is another type of thermal storage, costs around $40 per kilowatt hour. A battery storage will cost you $120 per kilowatt hour, right? So you can see the differences, how cheap we are, right? And we can also use the same storage to produce heat for industry, right? Because we're storing heat, right? Our lifespan is 35 years. We have no hazardous materials. We use air as our transport medium, right? So we don't have to have any special piping, right? With molten salt, they use molten salt is very corrosive, so they need to have special stainless steel material. For instance, there's a big power plant in Morocco, which they've had to shut down because the molten salt started leaking, right? With batteries, they have a life of about 7 years, so you have to replace them. You have to have air conditioning warehouses to house the batteries. So the cost of battery storage is very high. One of the things which I wanted to, okay, so before I go on to that, so what are the applications? So one of the applications is grid balancing, where the grid has too much energy and it needs to give that energy out to stabilize. So we can take that energy into the storage. We have a centralized power production, or we can have a decentralized power production. For instance, in remote villages, also remote towns where you don't have the grid connection, we can build a small plant, right? For industry, we can provide heat or steam. We can provide absorption cooling, water desalination, and enhanced oil recovery, right? And hydrogen production, right? So those are all the other vertical markets into which we can provide our technology. I just wanted to finally finish off with just giving some further details on our thermal storage. We've now modified the storage, right, where we can actually take the storage and use that to store heat from other sources, not just from our concentrators, but we can use the storage to store heat from PV, and wind turbines by using electric heaters, right? So the storage now becomes a hybrid storage where we can have different sources of power production, and we can put that all into the storage, which gives us then a base load power or a base load heat, right? So the idea here is that you can use different technologies for different conditions, right? So you don't have to have conditions of having sun 8 hours a day. You can have sun maybe 5 hours a day and a lot of wind, and we can combine a power plant by using PV, our solar concentrators, and wind, and put that all into the storage and then extract from the storage through using a conventional turbine, right? So that is an overview of what we do, right? So let me now see if I can stop this. Has that stopped sharing, or am I still sharing? Okay. Has that stopped sharing? Okay, stop. Sorry. Okay. All right, so that's a quick overview, right? I can go to as much detail as you like. So, we're open to questions.
So please, anyone have a question, you can ask. Only the technical, the funding and the stuff we talk about different time. Okay, please. Anyone have a question, please?
Yeah,
Oh,
Pat, Pat, do you want to ask? You want me
Yeah,
to ask?
absolutely. I was waiting for you respectfully, Chris, to start, but I'm going to start with
Go ahead.
a technical question about the temperatures at the storage. In battery technology, the BS battery management systems control just about everything that is temperamental to the chemistry of the battery technology, whatever it be, sodium, it doesn't matter, acid, AGM, or lithium. How does your storage management system control the thermal, I would say the thermal, what could happen or would happen in case of an overheat?
Okay, so the heat capacity, sorry, the temperature capacity of our storage material is 1700 degrees.
Okay.
Okay, so our normal storage temperatures are between 900 to 1000 degrees.
That's the perfect working temperature.
Right.
Okay.
And the reason for that is simple, is because, as you know, look, in business, the bottom line is no one is going to adapt to new technology unless it's cheaper and more efficient.
Yeah.
Right. So we've looked at this, and the cheapest and the most efficient element, or the cost, is when we're using conventional stainless steel. As we move it over 1000 degrees, you need specialized stainless steel, right?
Right.
And the price goes up,
Mhm.
right? So the optimum is 1000 degrees, right? But we can store at higher temperatures. Now, how do we manage that? We manage that by the flow of air, right? So, for instance, when we're producing 2000 degrees at our focal point, we pass air at a much faster speed to absorb that energy, so that air temperature is just 1000 degrees or 1100 degrees.
That's so it's almost like the faster you move that air, the
Correct.
cooler it becomes, and then it kind of centrifuges to the system.
Right. So, for instance, in the morning when the temperatures are much lower, the airflow is lower.
Got
At
it.
lunchtime, because the temperature is much higher, the airflow is much greater.
Okay, so now you're making sense. So there is it's almost like it is rocket science in a way, that you're basically you know how to thermal control that temperature to that perfect sweet spot. Yeah,
Absolutely.
I get it. Listen, it's the most amazing. It's one of the most amazing. The thing that I like about it was in the explanation about the glass manufacturing, like 1,000-year-old or 500-year-old glass manufacturings use this storage technology.
They use ceramic storage, but they use,
yeah.
So one of the problems with the storages is that you need to have a lifespan, right? Because ceramics has been used in glass industry and in the steel industry for years and years, right?
Yeah,
so
we're famous
they
for
have
that.
cycles every 5-10 minutes, whereas our cycle is one a day.
Wow. So that's longevity to the 35th
that
year.
gives you
Like,
the 35,
that's why.
40 years.
It's like it's like a discharge charge kind of cycle every 24 hours. So
Yes.
that's why you're getting 35 years. Back to the ceramic part of it.
Yeah.
Are these storage vaults underground, or are they above ground?
No, underground, we can't put them underground, but the cost goes up, right? So they're overground, they are insulated, right? And very little heat losses.
What is the temperature? So if the outside temperature, for instance, if we can get this outside inside temperature. So, we're always concerned about -40 below and then +40 above, as we're talking both from 40 degrees today and humidity here in Toronto. So on the scale of that, in insulating a ceramic vault, the ceramic vault has density, correct?
It does
Like
have
it has protection in its density.
Yeah, so the vault does have densities, right? So in essence, you have a chamber. In fact, you have two chambers because we can do
Okay.
simultaneous charging and discharging, right?
Yep.
Right. So you have two chambers, right? And you build the storage such that then you have a steel cylinder around that, and then you have your insulation, and you can touch the storage. It's not a problem, right? So the outside of the storage is ambient temperature. Right.
Got it.
So
Got it.
you
Yep.
can work at minus 40 degrees as ambient
Yep.
temperature, not a problem. You'll still achieve your 900 to 1,000 degrees inside.
Okay, so that is the real important factor here, because that density of the you call them bricks or the liners. I would call them liners. They are, like a blast furnace liner, right? That you would see at a steel manufacturing plant in Hamilton. They're all ceramic. They've got all that ceramic casting, right?
Yeah.
Like that. I've gone through a tour of that one in Hamilton, and it's
Okay.
just, yeah. So you make total sense about that.
Yeah.
Yeah. When I say about above ground and subterranean, wouldn't it be beneficial to bury the vaults, or not to bury them, but to have them subgrade?
Okay. In terms of on the technical aspects, makes no difference to us, right?
Right.
It's all about cost, right? And
It's
if the land is above ground is very expensive, then
Yeah.
obviously it makes sense to bury the storage. But if it isn't, you have the storage outside.
the thing, though. What I'm thinking about is metropolises like the city core. There's going to be so many buildings taken down in cities like New York and Chicago. Like, we are literally taking down buildings. We're taking down 20-story buildings to build 100-story buildings.
Yeah.
So again, these are the cities of the future.
Yeah.
So again, I see the vaults. I see the vaults in the ground underneath. You know what I mean? In the parking areas, or you see where I'm coming from?
No,
Yeah.
I see what you're saying. Our focus has mainly been on
Okay, guys, we must give time for other people if they have a question.
Sorry, yes, I appreciate. No, I understand. I appreciate it. I will yield to the group. Thank you. And thank you for taking that time. It's very, very interesting.
Yeah, Mr. Amarjit, is this commercially readily available, or is it in the trial stage?
No, we have a pilot completed in Spain at the CMAT Institute with a 3 megawatt hour thermal storage, and so we also have in India we have interest from a number of companies who actually are ceramic manufacturers, right? Because they have a problem because most of them are using gas and oil to produce the sort of 700-800 degrees temperatures that they require, and so that is expensive, right? So there's a lot of interest in India from ceramic manufacturers for just the storage, right? So that they may be using, they may use the concentrators, they may use PV. It doesn't matter, right? But the concept is the same.
Okay, and one more question. Can you share us the what all configurations are available for this product? I mean, there are, I think, 4 varieties are there: 6 meter, 10 meter, 15 meter, and 26 meter.
Yeah.
So, could you share me some more information on this?
Yeah.
And typically, what is the land size is required for 1 megawatt installation?
Okay, I will put together a data sheet and I'll get that across to Sam and I can send it to you.
Thank you. Yeah. And could you indicate what is the cost of the 1 megawatt, if you don't mind? ROM price.
it's very difficult to give you a general
I
price,
understand
right?
it. Mm.
Right. And I think what I would say is that you need to give us more of the location so
Mhm.
that we can work out. For instance, if I give you an example, right? And I'll give you an example on PV, right? So if you have PV in a location where you only get sunlight for 6 hours, right?
Okay.
And you have and compare that to PV where you have sunlight for 10 hours, right? So for the same production, you're going to have a lot more PV in the area where the sunlight is much lower, right? So the cost is much different, right? And it's same here, right? So here, what we're doing is we're saying 1 megawatt, 24 hours a day, 365 days a year, right? So we need to know the location, right? Number one, so we can work out what the radiation is, and then from there we can then work out some initial costings. These will be very rough costings.
Correct. Yeah. Got it. Thank you.
Okay, somebody ask question. Somebody have a question, please?
Yeah, I'm just Chris. It's very exciting, particularly the storage side of it. What I want to ask you is, you're saying that 0.5% to 1% loss. Can you tell me how long that half or 1% on what period that loss will be?
Okay, so so when I say 0.5% loss a day, so you lose about
Is it per day?
per day, right?
Oh, 0.5% per day. Okay.
0.5% per day, right? But on what I was saying was on the larger storages, you can get losses of 1% a week, right?
Okay.
Because so if, the loss is determined by the surface area of the storage.
Yeah.
Okay. So the surface area is your radius times your whatever it is, the
Yeah,
area.
yeah,
Right? So
yeah.
what I'm saying is the volume goes up at twice the rate as the surface area,
Okay.
right? So the bigger the volume, right, the surface area is not a linear correlation,
Yeah,
right?
yeah,
Because the
yeah.
volume is radius squared, right? So the bigger the storage, the less the losses. The smaller the storage, the greater the losses. Okay,
Okay.
number one. Number two is that it doesn't really matter. If you're charging it on a daily basis,
Yeah,
that 0.5% loss is insignificant to your overall energy losses anyway.
yeah. For daily managing, massaging the power, it doesn't really matter
It
0.5%
doesn't matter.
or
And number two is if you're looking at data centers, right? So one of the biggest consumers of the power in the data center is your cooling,
yeah,
right? And not just running the processes, right? So with our storage, essentially we have again, this comes to economics. It's more economical for us to waste some of the storage heat at 100 degrees or 1200 degrees, right? Rather than capture it. Okay. So the waste heat from the storage when we extract energy is around 100 degrees.
yeah,
Now that can be used for absorption cooling. So in other words, that we can provide you in a data center both with power and cooling
yeah,
from the same storage.
yeah. And my question is the economics of it. For example, if you do the battery storage, particularly if you have to convert into electricity, let's say from PV to battery, you're directly charging the battery, and then when the demand, that's how the data centers work nowadays. When the low cost electricity time. For example, in Canada, the peak time is 11 cents. On the off peak time is 3.5 cents. For a lot of people are using the batteries. to charge it at 3.5 cents to deplete it at the 11 cents time. So that itself is a cost center for them. Although battery is $120, that I don't know what's the efficiency. If it is only electricity, if it is cooling and or providing heat to some factory, that's much more efficient. What you are saying, but if it is a data center purely for electricity, what is the efficiency after storage to all the way to electricity type of thing?
Okay, so the efficiency
So
very
we
much.
have a kilowatt hour of energy stored, and what will be the output as an electricity through this generator and everything?
Okay, right.
What
So
you know what I'm saying?
I
Yeah.
know what you're saying. I know what
Yeah.
you're saying. So the efficiency is dependent on the size of the turbine, right?
Yeah.
So if you're looking at a 1 megawatt turbine, the efficiency is about 25%. So you're
Okay.
losing 75%, right?
From storage kilowatt hour to the electricity kilowatt hour. Okay.
Right. Now, if you're looking at something like a 10 megawatt,
Yeah.
right, the efficiency is about 35%, right?
Okay.
If you're looking at a 50 megawatt turbine, the efficiency is about 45%.
Yeah. Depending on the size of it and all. Okay.
Right. So the advantages where we see this happening is taking that cheap electricity, right? So one of the ways to do this is take the cheap electricity and offer you power as well as cooling, rather than using the power to do the cooling, because power is a very the energy in terms of, if you're looking at the spectrum of the energy, power is at a much higher end of the spectrum than heat, right? So if you're using then the power to do cooling, it's cheaper to do the cooling with the heat rather than the power, the cooling, right? So again, it's something that can be done, but it needs, you would need to do an exercises to see what the efficiencies are and what the economics are.
No, I understand how to optimize is different, but of course you have to design the system right from the beginning. And in general, like in the USA or Canada, the data centers designed a grid power.
Yeah.
Therefore, right now we are using batteries mainly for a backup. Plus, we are using the diesel for a backup as well.
Yeah.
People are using battery for as a cost. When the low power is at 3.5 cents, they load up the batteries and then they deplete the batteries. But it's expensive, as you say. It's $120.
Batteries are expensive.
Batteries are expensive. It's just not the battery alone is the cost. It's the overall, depending on what you are using for, the overall efficiency of it. That makes the capital cost. Yeah.
Yeah. Batteries are expensive. Right?
Yeah.
And then you have to replace them every 7 years. I mean, that's the other problem.
And what you're saying is correct, that the amount of space required for the whole system, from concentrator to core, all the way, is depending on the radiation level in each country, which will be. Again, one more efficiency again is from the concentrated solar efficiency to all the way to storage. Versus PV system to storage. Is it a similar efficiency as well, the conversion?
Okay, so with the concentrated to storage, you're losing about 10%.
Okay.
Right. Because you've got the piping, and so a large power plant is going to the storage. The concentrator is going to be over a vast area, right?
Yeah.
And so there are losses there, right? With PV, for instance, if you're looking to use PV and put that with electric heaters and use those to heat air into the storage, right? As I said, that's another way of charging the storage. Then the losses are less than 2%. It's it's got about 99% efficiency of converting electricity into heat into the storage.
Wow.
You use resistive heaters, right? So you don't actually need inverters on your PV. So you can use resistive heaters directly, and so that brings the cost down of the PV and the cost of production anyway.
Wow. What do you think of that, Chris?
Yeah, it's a more efficient places like Arizona, Phoenix. Those areas are becoming the center for data centers now. And there it's really efficient.
Yeah, absolutely, and especially where you've got a lot of land with the data center. Right?
Yeah.
So you can have your own PV plant, right? And then your own storage, and then a turbine, and so you get 24/7 and cooling.
Yeah. I know somebody from India, but India is a good place. Bangladesh is the whole area anyway. Yeah.
Africa.
Africa is.
Oh my God, the mining in Africa.
It's huge. It's huge.
Yeah.
Yeah.
And most of the power for mining is required for cooling, actually.
Yeah.
They need heat. For instance, in copper mine, they need a lot of heat. But a lot of the power is for cooling.
Yeah, exactly.
And when you're transporting diesel 200 miles, it costs a lot of money.
Okay.
And it's lucky if it gets there, if it's not hijacked. Sorry, I just had to throw that in.
Are you making the storage as a modular system so that if you want a 100 kilo?
We have to see it.
Yeah.
Yeah, it's a modular system, right?
It's a modular system.
We have, so if you want, for instance, if you want 50 megawatt hour storage, it's 5 10 megawatt hour modules.
Okay.
Right? If you want 100 megawatt hour storage, we will give you 5 20 megawatt hour modules.
So you've got them cubed. Yeah.
So the idea is, everything is done in the warehouse and the factory.
Yeah.
So it's transported to the location and simply assembled, right?
Yeah.
So we have a lot of control on the build, right? And to minimize any issues when at the site, right? So everything is controlled in a controlled environment, built, tested, and then shipped out, and it's assembled. Literally, the storage is assembled by nuts and bolts.
Meccano, simple Meccano.
Yeah, it
very,
is.
Very well. It's that your simplicity rings many bells to me, because that's where we started. You could over design a system, but it's not necessary. It really isn't necessary.
It isn't.
You can build a 1 to 10 instead of a 1 to 100 assembly, instruction manual.
There's some of our competitors, for instance, they have a thermal storage, and what they do is they have their heaters inside the storage, right? Our heaters are outside the storage. So if one of the heaters breaks down, you simply change it.
Yeah.
If they're internally, first of all, you've got to cool the storage, right? Then you
shut
replace
it down,
right? So that may take you 3 days if it's a large storage just to cool down.
Yeah. That ain't going to happen at BMW. They're not going to shut anything down for 3 days. They won't even shut it down for 30 minutes.
No.
Okay.
Majid, can you allow a prospect to see the site? I mean, install prototype site.
The one in Spain.
No problem.
There is a pilot site in Spain. Unfortunately, the thing with that one is it's now closed. It's still available. But if you want to see the concentrator, we have concentrators in Serbia, right? So you can come. You're more than welcome to come and view that there.
Fantastic. Okay, thank you.
Okay. I just have a question though, Chris. Sorry to jump in like that. The people that are manufacturing the bricks for the storage vaults, basically that mechanical end of it, is there anything that is in a prototype state that is working?
Yeah. I mean, okay. So the bricks that we've got are manufactured by Saint Gobain.
Okay.
Right. So it's not that we have a patent on the.
Well, you buy bread, 5 cities, eh? So they are working. Buy bread, and then you buy this. You don't like who? You don't like it. Okay, they will buy.
Okay.
So what I was saying was the ceramics are available from many suppliers.
Please, guys, if you don't talk, just close the mic because don't mix. Can you just close the mic?
You bring one stream. Since this alone is not there, what I asked for, and before I bought that new and you can't bring one stream. Now we are carrying it on the back. It's really said now that you use. Sit down, it's really said down.
Okay, so any more questions?
Well, I just wanted to, my question is, is there a physical location of a storage unit in use right now?
Okay, so there isn't a physical location of storage in use right now. There was a physical location. It's still standing at the CIMAT Institute in Spain.
Okay.
Right? But that was used to do all the testing. So we have all the test data, we have the report, right? So that is all available. The ceramics, as I said, are simply purchased from Saint Gobain, and there's another supplier, right? So so this is a ceramic which is off the shelf currently, right?
Okay, but the location in Spain, if we were to tour that facility where that inoperable now storage vault is, would that give us the physical, that you're physically standing in front of this thing, understanding the scale of it?
I'll send a video to Zad. I think Zad's got a video. He can share a video with you, right? Number one. And number two is that that we will be looking to build a pilot anyway, as a demonstration pilot to showcase the technology. So you'll be able to see those using the concentrator, the storage, absorption, cooling, and power production.
Okay, and when will that be produced?
Well, that will be probably early 2027.
Early 2027. Okay, well, it seems like we're all aligned. We're all on the same time link, and this is exciting. It really is.
And we're going to have a similar, same time we build our factory in Oman, we're going to make a small model.
Mhm.
So,
Yeah.
for the engineer, the people that are interested in open the factory, we're going to do same time. We build a small model in the factory. I think we share the design. We're going to have a class for the engineering, how they work, how they.
Yep. Yeah. You're going to
You know,
train the tech.
we have to build up the skill set. So the
Yeah.
idea is that we will build one unit,
Yeah.
complete from collection to power production and all the ancillary elements with the storage. Number one is obvious to gain experience for the new staff members, and also there are some modifications which we've now made to the storage, and we want to implement those as well as for the concentrators.
In the solar end of it, just for a quick question, we're going through a solar retrofit now. It seems that solar is reinvented every 20 years. It's been a long time. We're in the second cycle of solar. And the form of crystallization in the PV and the efficiencies that have like changed in just the last 5 years, do you see that your units could be retrofitted with the new technologies moving forward every 5 years, 10 years, 20 years? Can you just like retrofit the unit to the new solar with the new solar panels?
Yes, you can.
Hey, Amarjit, good morning to you. Hello, everyone. This is Antonio Kraus. I'll take this question if you don't mind, Amarjit.
No, no
Thank you.
worries.
Okay, great. So just to address your direction here, okay? When it comes down to PV, definitely PV, it ain't a competitor to solar concentrated power. This is one. Secondly, PV as a general technological approach, yes, it is highly inefficient. It does not really matter what type of adjusting to the technology will be taking place. It doesn't really matter if they are going to be using any type of enhancement within the capturing and the conversion to electricity. PV is highly dependent on two solar radiations. That's all. So we are very familiar with developments into all types of new geometry, all types of films which they might claim enhancement within the production of the PV panels. But you need to remember that PV, it is highly limited to a window of production, and they are highly dependent on the type of sun exposures they get. Whereas for us, because we are actually converting directly to thermal values, we are not limited to only two types of radiations. As long as the sun is up, we will be producing thermal values no matter what. They might not be as high on an overcast day. They might not be the thermal values, that they might not be as constant during a storm, but nonetheless, we are going to be producing thermal values. So this, it gives us an edge and advantage, because those thermal values, it is much more easier to store thermal in any type or format. We are using the tiles to do that storage. But at the same time, it is way cheaper, longer lasting in storing thermal values than storing electricity. So this is the reason for which we can deliver not only energy in the format of base power, because we are converting all of the thermal energy in steam, and we are using the oldest form of producing power, which is steam generation, and hence we are producing base power into the grid, and we are producing in tandem with the grid, but we do have various other applications. We can produce for you the thermal values necessary to use steam in different industrial processes. We could plug in directly into the central heating or the central cooling within an installation, be it may industrial, commercial, and so on and so forth. So we are more versatile. So when your question was asked related to how we are going to be advancing from version 1.0, which we have deployed about 22 years ago, and it was a massive solar concentrator, which weighed about 26 tons. It was, Amarjit, something like that.
Yeah,
it was
22. Yeah.
Yes, we already are on version 4.0, and not only that, we have reduced the size and the weight of the solar concentrator, but we have improved the ability and obviously the angles on the mirrors and our medium of collecting that thermal energy greatly over the past 20 years. And we do believe that we are on the verge on further improving the solar concentrator design and the way of disposing it, deploying it within the field in such a way to increase in the upper northern regions the ability to collect even more thermal energy, comparing with the thermal energy and the design which is going to be used towards the tropics or the Ecuador. So yes, to answer your question, definitely we are going to be adjusting continuously those designs. We are going to be improving on them, and in the next 3 years, we believe that we are going to have an even more versatile product which we are going to be deploying out there.
Thank you. That was very thorough. Thank you for that explanation.
Amjit, this is Chris again, and one of the thing that we are not able to kind of get a feel for it is this whole capital, how much money you have to spend. For example, 1 megawatt. I know you are saying that if you're doing in Canada versus Africa or India, it's all different. The footprint is, the amount of area required is different. The number of panels required is different. Everything is different. But is there have you people gone through this? That I'm talking about all the way, not just the heat generation used for heating something or making it as a coolant, cool. But I'm talking about all the way to electricity.
Okay.
For 1 megawatt, let me finish it. 1 megawatt, for example, if you do a sun a certain amount of hours and things like that, certain locations, at least 3 or 4 locations, what would be a 1 megawatt total cost of it? And then you can also what's the cost of electricity per kilowatt hour at the end of the day on an average 24 hours a day or whatever. This is the part kind of I'm not able to get a feel for it.
Okay, Zad,
1 megawatt, how many millions of dollars it costs?
Yes, Please, today only technical. Tomorrow we have meeting about hydrogen. We going to get everybody the detail, how much cross and how this detail, the financing, okay? And also, I just want to say something. We are already open and we want to do a lot of homework and build a project, but we need a proposal from the people when we want to do the deal as an investment, or the people have a funding to put on the ground for the factory or building station. For us, tomorrow they're talking about it. Today, only the technical.
That's
Only
fine.
the
That's fine.
Thank you.
Just something that we would like to know. That where we are considering, we are thinking about USA, certain locations, so that we can understand how it compares to other systems.
Of course, tomorrow decide. Today, only the technical
No
stuff.
problem. No
Okay,
problem.
thank you. Okay. Anyone have a question, please? Tomorrow we're going to have a meeting about the hydrogen also with the engine, and we can talk about the cross for the megawatt and everything. If we don't have anything, we can stop until here. If
Okay.
anyone have a technical question, today only technical question.
Okay, I would like to add something to the technical aspect, which I believe it is very relevant, in special taking into account the destructive nature of all of the so-called green energy solutions. And I'm not going to limit this only to the photovoltaics, but to the wind power as well, and some other so-called green technologies. We need to keep in mind here as I don't know, project developers, project financing teams, local municipalities, governments, and overall as business people, that what it has been proven so far, and it is a message we have been pushing, at least myself and the team for the past 20 years, is that photovoltaics and wind, they have massive, and they carry massive carbon footprints, but they present a massive hazard to the environment and obviously to the projects themselves. And slowly, the industry starts to wake up to the fact that all of these panels, once they reach their end of life cycle, or once they get damaged, it is very difficult to dispose of. I'm not sure if any of you are familiar with these massive dump grounds where panels are laid down to rest, and this is pretty much all they are exposed to all of the environmental factors like rain, sun, cold, hot, and so on and so forth, and they are slowly degrading and poisoning all of the immediate environment, and now they are seeping all of those metals and chemicals into the water below. Our technology carries a massive advantage. We are building using two main, let's call it two main materials. One of them, it is steel, which it is making up about 97% of our solar concentrator, and about 3%, which it is aluminum mirrors. So as you could imagine, our products at their end of life, which is not going to be 15, 20, 25 years, end of life, it will extend to about 50 years. They are fully integral, recyclable. So pretty much we are not going to leave any type of environmental footprint at the end of life. As a secondary aspect, you need to remember that PV same as the wind turbines, they are a hazard to the environment, a continuous hazard, because the way how PV is deployed, pretty much all of the soil on the soil where the farms are being deployed and the immediate vicinity of that soil, they will suffer greatly soil degradation because of the proximity to the surface of the ground, massive thermal values, the soil gets deteriorated, and at the end of lifespan of a project, you are going to end up with a brownfield rather than something which can be reused, which is going to be very, very costly. For us, the solar concentrators, they are pretty much operational at about 7.5 meters above ground. So we are actually contributing to the protection of the soil beneath. At the end of the day, an entire solar concentrated power farm upon deployment, and once it is put back, once it is put in operation, all of the land beneath the installation can be used for mixed farming. It can be used for animal grazing because of the shade we are going to be projecting onto the ground from all of the solar concentrators. The grass, it's going to be thriving underneath, and pretty much the soil, it will be very, very rich in all of the fauna of the soil. You can do grazing, you can do limited format of I don't know, agricultural production. So pretty much we are not interfering, or we are not destroying with our footprints the soil on the deployment. On another note, and a very important aspect, it will be that all of the area where the solar concentrator will be deployed, it will actually maintain a microclimate, because we are collecting all of that waste thermal energy. We are not creating waste thermal energy through reflection or through covering of the soil. Pretty much you are creating a microclimate, a microenvironment, which is going to be very beneficial, not only for everyone around it, the solar farm, but it is going to be very, very beneficial for all of the land where the deployment takes place. So these, I believe, they are very important aspects which they need to be considered in the grand scheme of things.
May I ask a question? Is this technology applicable for over water?
Okay, what is the context when you are talking about water?
Coastal installations.
Yes, definitely we can do deployment within coastal areas. We will need to do adjustments to the architecture of the deployment itself based on the humidity, the constant humidity associated with these areas because of the seaside. But definitely, beside the fact that you are going to get an easier deployment, because everybody needs to remember our footprint in the ground is going to be about 4 square meters. So we are going to be laying down a slab of concrete, and we are going to be attaching the solar concentrator on top of it. So you are not going to be facing all of the deployment challenges which coastal areas are posing to different other type of technologies, photovoltaic included. So yes, it will be very beneficial and very easily to be deployed in coastal areas. And
can it be installed on the rooftop for the existing building?
very difficult to make a technical assessment up until such time comes that we understand the area surface of the building and we understand the gravel engineering part, the structural part of the building, so we can make an assessment on whether we could be deploying on those roofs and how many units we could be deploying on those roofs. There is a two-part component, but theoretically, yes, we can deploy. Now, would any building would be suitable for a deployment? We'll need to do an independent assessment of that building per se.
Thank you. Thank you.
Okay, so anyone have a question? Or we stop until here. And tomorrow we start different for the hydrogen and we talk about funding and the cross and more detail. And I'm going to share with you more detail in the evening. So tomorrow when we have meetings, so you have more idea what we can do.
Sure. Okay. Thank you.
Okay, thank you.
So the
Thank
time,
you.
so the time okay for you guys because people stay very late, you know.
Well, it is what it is. It's okay.
It is what it is, but we'll all meet in somewhere in the world all on regular time and we'll have lunch.
Okay. Tomorrow,
Okay.
tomorrow we're going to have more detail and actually we want to do something very good for the future. And we want to use all the natural. So tomorrow we can meet. And thank you for your coming and same time tomorrow. Okay?
Thank you.
Thank
Thank
you.
you.
Thank you
Thank
for
you.
hosting us.
Thank
We
you.
appreciate it.
Thank
Bye.
you. Okay. Thank you.
Good night.
Bye-bye. Bye-bye.
Thank you, Antonio. Thank you, Mr. Amarjit. Thank you.
Bye-bye.
Bye.